All right, welcome back, guys. I'm sure that there have been some sleepless nights after our last entropy lecture because some things you've been mulling over, some things in your mind, and you're like, "Wow, that doesn't make any sense," right? So we're going to talk about some of that. I know, don't try and tell me that you don't think about chemistry all the time. I know you guys better than that. But anyway, changes in entropy. Okay, we talked about the first and the second law of thermodynamics last time, and one of the things that we said regarding entropy is that entropy increases as a substance goes from solid to the liquid phase to the gas phase. Each time it hits one of those phases, entropy increases. So let's think about that for a moment. What that means is that if you, for example, for water, right? If you have ice that melts and turns into liquid, that means the state of the water in its solid phase at the beginning was had less entropy than water had when it converts to the liquid phase. And so the entropy at the end of that process is greater than the entropy at the beginning. And so in that case there, that would mean that the overall change in S would be greater than 0 because you got a bigger number and you subtract from that a smaller number as far as the entropy, right? And so that's fine because if you remember what the second law, I'm just going to abbreviate it this way. The second law of thermodynamics says, we said we could sum that up by this statement here. Change in S for the universe is greater than or equal to 0. Things aren't getting more orderly, they're becoming more disorderly, all right? Well, so this is fine if you go from solid to liquid, right? That's the case. Or if you go from liquid to gas, that would be the case because you've got a larger number for entropy minus a smaller number. But what about when it goes in the other direction, right? What if water is a gas and condenses into a liquid? Well, in that case, if you go from a gas to a liquid with water, what you have is a change in S that is less than 0, right? Because now you've got a smaller number because the final state is liquid, and you subtract from that the larger number because the original state was gas, and so the change in S for that liquid is less than 0. That's the stuff that was keeping you guys up last night. I know that. You were like, how does that go? How can I resolve that with the second law of thermodynamics? See? I knew you were thinking that. Well, it's still okay, and I'll tell you why. Because, remember, we talked about before what happens when water, for example, freezes. When water freezes, it's got to release energy, right? And it releases energy in the form of heat because it's getting colder so that it can freeze. And so when it freezes, what it actually does is it actually heats up its surroundings, right? Because it's released some energy in order to do that. And so when water goes from gas to liquid, or when water goes from liquid to a solid state, because it's releasing energy into the surroundings, the entropy of the surroundings actually increases. Right? So you can't just look at, when you consider a system, you can't just look at the entropy just for that system. You have to consider also the entropy for the surroundings of that system, okay? And so as it turns out, this is actually the proper way to think about it when you have something like water change in phases or any substance, right? That the change in S of the system plus the change in S of the surroundings, that has to be greater than or equal to 0. Let me put a line through those like I like to do with zeros so that we don't forget that that is a 0 and not an O. So this, by the second law of thermodynamics, has to always be true, right? So that's what we got to make sure that we consider. Not just the change in S of the water, of the liquid, of the gas, whatever it is, but also when there's a change in entropy there, what's the change in entropy for its surroundings? And this will always be true. If you add the two together, you'll always get a value that's greater than or equal to 0. Okay? All right, so let's consider what that has to do with a chemical system, a chemical equation specifically. All right? So because of the second law of thermodynamics, what that tells us then is that if we have a reaction, then the change in S for that reaction, right, plus the change in S of the surroundings has got to be greater than or equal to 0. All right? And so this has to be true in order for that reaction to happen. If this equation is not satisfied, then that reaction will not happen. Okay? And so then what we need to talk about now is we need to figure out how are we going to determine the change in S of the reaction, right? So we'll start off kind of simple. And instead of finding the actual change in S first, what we want to do is just see if we can determine the sign, okay? The sign of change in S. And I want you to remember a couple of things that I finished, a couple of points out of the 4 points that I finished the last lecture with. And number 1 is this, that entropy, and we just said this, entropy increases, right? Entropy increases, let me say it like this, entropy is greatest, it's greatest in the gas phase and least in the solid phase, right? And so we said that just a moment ago, that as you go from solid to liquid to gas, entropy is increasing, right? So we want to remember that point. And then the third thing that in the list of 4 points about entropy we made last time was this, that entropy increases as the number of molecules increases, right? All right, so by remembering those 2 points there, we should be able to determine the sign of the change in S for a particular reaction. And I just want to mention this. Number one is more important than number 3. All right, so as we're using these rules here, if number 1 and number 3 apply, number 1 is the one that's going to have the greater bearing on the change in S. Okay. All right. So let's do a couple of examples. There's 3 examples under example 14.5 in the book. So if we'll look at those, the first one says, determine the sign of change in S for the following reaction. Determine the sign of change in S for the following reaction. It gives this reaction, 2H2O2 in aqueous form yields 2H2O in liquid form plus O2 in gas form. Okay, so let's think about that for a moment. Aqueous, we know this is going to be, it's dissolved in water, so we could consider it to be in the liquid phase. This one in the liquid phase also, but this one is in the gas phase. And like we said, that was point number 1, right? As you go from solid to gas is always going to have a higher entropy than solid or liquid does. And so that's the point that is more significant when figuring out change in S, right? And so what that means is that you've got higher entropy over here on this side, and you've got a smaller number on this side. So a higher number minus a smaller number is going to equal a positive number, right? So change in S, let me just write that out so that it's not confusing. Change in S is positive in that case, okay? All right, what about the next problem? The next problem wants us to determine the sign of change in S. Again, the sign of change in entropy, and this time we're given another equation, 2CO in gas form is going to yield, in gas form plus O2 in gas form reacts to produce 2CO2 also in gas form. So here, everything is in gas form, right? So the phase isn't going to help us that much. So we got to look at the other point. And that is, the more molecules that you have, the greater the entropy. So on this side, we've got 2 CO molecules and 1 O2 molecule. So we've got a total of 3 molecules. On this side, we only have 2, right? So S is greater on this side, right? And so you're going to have a smaller number minus a larger number. And so the total change in S then is going to be negative, right? A smaller number minus a larger number is going to be a negative number. And then finally, one final problem. It says MgCl2 in aqueous form plus 2 KOH, also in aqueous form, is going to yield MgOH2 in solid form plus 2 KCl in aqueous form. All right. So in this particular case here, just as a quick glance, we've got one molecule here, 3 here. Here we've got 2 here, total of 3. Here we've got 1 molecule and 2, a total of 3. And so the final, the number of molecules then is not going to help us at all for this particular problem. What then we need to look at is the phase for the substance. And so in this case here, we've got aqueous, aqueous, aqueous. We've got one solid. Solid we know has the lowest entropy. So what that tells us is that on this side, we've got higher entropy, right? So higher entropy on the left side, lower entropy on this side. A small number minus a big number is, again, like with the last problem, is going to give us a change in S that is negative. All right? So that's it. That's all we really want to be able to do right now. At this point, when you're figuring out the change in S, the change in entropy, is it positive or negative? And so hopefully you have the tools now to do that. All right? See you in the next lecture.
This concludes this session of Chemistry with Mr. Walker. If you'd like to watch more videos on this YouTube channel, we recommend watching more videos on this YouTube channel. Thank you.